Cold spray of aluminum powders is heavily influenced by the native passivation layer that must be fractured for metallic bonding to occur. Although only several nanometers thick, thickening, hydration, and partial crystallinity has been observed to increase the critical adhesion velocity in powders treated under humid conditions. However, it remains unclear which of these three or some combination are principally responsible for the observed increase. Unfortunately, experimental characterization is extremely difficult due to the length scales involved. Moreover, alumina is known to exist in a multitude of forms, including hydrated, crystalline, and amorphous phases. Furthermore, empirical force fields, isolated systems, or varying simulations parameters inhibit direct comparisons of existing computational work. Fortunately, empirical relations have been developed to relate the critical adhesion velocity to the Spall strength of the particle-substrate interface, and under the assumptions of sufficiently high strain rate, the Spall strength is proportional to the bulk modulus. Here, ab initio calculations using density functional theory and VASP are employed to determine the bulk moduli for the majority of alumina phases. Unit cells of crystalline phases, including oxides, oxyhydroxides, and hydroxides, are collected from literature and underwent static relaxations, after which homogeneous volumetric strains are applied to generate the relations of energy and volume, from which the bulk modulus is determined by fitting the Murnaghan equation of state. Amorphous representative volume elements for each composition are generated by a melt and quench method using a react-FF potential incorporating alumina ions, and subsequent DFT relaxation. Averages for 20 simulations of each volume of amorphous structure were used to fit the equation of states, since the canonical distribution can be described as the average of smaller cells. As expected, results indicate that the alpha alumina and amorphous aluminum hydroxide had the highest and lowest bulk moduli respectively. Likewise, the bulk moduli do not appear to differ significantly between crystalline oxides or oxyhydroxides and hydroxides. Rather, crystallinity plays the strongest role in affecting the bulk modulus. Shock relations are used to model the critical adhesion velocity under the condition of spallation at the interface during jetting. Jetted material is assumed to undergo pure tension as pressure is released at the free surface, thus the dynamic strength is approximated by a rule of mixtures. And again, for sufficiently high strain rates, Spall strength is proportional to the bulk modulus. As can be seen by estimates of the change in critical adhesion velocity for humid treated powder compared with the thinner amorphous oxide passivation layer of the untreated powder, a fully crystalline passivation layer, regardless of composition, would significantly increase the required velocity of the particle. Additionally, amorphous oxyhydroxide and hydroxide passivation layers would result in a lower velocity despite the oxide being thicker. Even a fully crystalline oxide, or oxyhydroxide or hydroxide passivation layer, would increase the velocity well beyond experimental observations. Since the thicker oxide is known to only possess rare inclusions of crystallinity, the more likely explanation is that thickening and partial crystallinity are primarily responsible, while humidity only accelerates growth of the native oxide at low temperatures.